Is okay. Right. So there are few factors, okay, affecting the signal generation. Okay, I think I have mentioned the signal that you obtain, for example, current change, color based, fluorescent based, the changes that you observe, okay, will be affected by certain factors. One is non-specific binding. Okay. So what is non-specific binding? But I mentioned last week. What is non-specific binding? Anyone? Ahmed, you usually speak up. What is non-specific binding? Are you there, Ahmed? Anyone? Everybody is going
Not suitable with binding that we want to attach. I mean
uh-huh.
the the bind, not the specific like we want the required one.
I,
Other substance.
yeah. I understand what you're trying to tell me. Okay, it is correct. Okay, so you imagine the DNA. Okay, you imagine the DNA. Remember about the probe DNA that we have obtained, which is now the sequence are specific to certain other DNA that we target. Let's say dengue virus DNA. So this one is a standard probe, bukan standard probe. It's a specific probe, yeah, specific DNA probe. Okay. Now, if you imagine the blood samples that you obtain from you, like, for example, and that blood samples, of course, not just containing the dengue virus DNA that match with this probe, they also contain other proteins, right? Because you're talking about a complex sample. You're talking about blood. You're talking about saliva. We are talking about um, sputum. You're talking about tears, urine. Of course, there are so many other things inside that samples. So the issue with proteins or these biomolecules, they are full of charges, negative charges, positive charges. So even though you don't want other proteins to interact with the probe that you specifically put on the surface of sensor, you have difficulty because other proteins, let's say you have A protein, B protein, and since they are charges, they have charges, some positive, some negative, they still want to be on top of this surface. And they probably want to interact with the DNA on the on the sensor surface, which we don't want. Okay. So the issue of non-specific binding, if there is non-specific binding, then it will interfere with the final signal, which we don't want. So, Amira, you're right. Okay. I understand what you're trying to tell. Okay. But everybody needs to understand what's the issue with non-specific binding. Okay. We do not want this. We do not want this. This is a big issue. Okay. Remember that because everybody, I think, has used this COVID test strip. Yeah. If you read the instruction well, okay, one of the instruction is you better, like if you eat something, you better rinse your mouth or avoid eating. Okay. You must make sure that your mouth is clean before you test your saliva. So this is to avoid non-specific binding, because if you eat, then you are adding more proteins or uh, more compounds in your saliva. Then you can imagine how difficult it is for the sensor to just specifically interact with the uh, virus rather than interacting with other kind of materials in your saliva samples. So this is a big issue. Okay, so there are ways to mitigate this issue. Means that you cannot resolve 100%. There are ways to uh, reduce the effect of this non-specific binding. Okay, that is number one. Okay, number two, what do you understand about, even though I didn't mention last week, the density of these biomolecules? Anyone? Well, it's week 5. I wish to have more interaction with all of you. What does it mean? Okay, Amira, she has answered. Probably someone else? And anyone else? You still driving? So if you look at here, okay, uh, this is the one that probably much better, or yeah, okay, let's put it here. Okay, now, can you spot the biomolecules? Which one? The DNA, right? The that looks like a spring. Okay, I hope that you can spot that. All right. So what does it mean of the density? In this case, we're talking about DNA, so it can be about uh, antibody. Is the spacing of the biomolecules on top of the sensor surface. So which one is better? You want to put a lot, like very dense, or you want to space out? Okay. Okay, this will affect the signal as well. Same goes to other molecules, other biomolecules. You probably think that if you put as much as antibody on top of the sensor, it might give you a good signal, but that's not the case. Sometimes it actually give you a bad signals. Okay, so this is what we call as probe. Probe means the DNA, protein. If you're working with protein, like enzymes, okay, antibody or aptamer. I think by now you should know all about this. Okay, antibody, aptamer, density. So that is the meaning of density. How much you want to put on top of the sensor surface. If you really need to put a lot, you have to think about the surface area. How much area of sensor surface that you have. Because one thing about when we talk about protein, because those are all amine, carboxyl functional groups. And they, as I mentioned, they have charges, positive charge, negative charge. So they might interact with each other. And we do not want them to be in that situation. We want them to be very nicely uh, separated, okay? We don't want them to get tangled because we want to make sure when the, let's say, DNA comes to the target DNA comes to the probe, they have enough space to interact. And let's say you have the antigen. I hope that you know what is antigen by now. they have enough space to interact with the antibody. So the density or the how much you put on top of the surface is very important to uh, optimize. Optimize means you have to study how much. You don't know how much actually. So we need to study. We put them and look at the signal and then put them, increase the concentration, whether we get a good signal. And then we do things uh, repeatedly, whether we have the same signal. So it's actually a lot of work to do that. Okay. But it's something that we must do. And then what is linker? Okay. So here, if you look at the picture, all right, let me clean up a bit. Mhm. What is this? Eraser. Okay. All right. Okay. So now you can see that this is the bioreceptor, right? So what are the extra things that you see? Those are what we call as linkers here. And why do we need linker? Okay. So I hope that you still remember when we talk about accessibility. I think last 2 weeks. Oh no. Last week, I don't remember. Uh yeah, last week I think. If you go to the shopping complex, okay, buying, yeah, Hari Raya clothes or whatever. When there are too many people, you actually you went together with your friends, and because everybody wants to look at other things, not the same things. So, but you need to find them. Okay, so I mentioned that last week. Okay, so your friend must be accessible. So if your friend is taller than everyone else, of course, it's going to be easy for you to recognize your friend because he or she is taller than everybody else. Then you can see and just go to them. All right. So let's see what happened if your friend is here and is shorter than anyone else, than everyone else, then you have difficulty. So this is the one that we call, this is the need for linker. So there are some, uh, you can see that there are different size of linker here. Okay. So we need to study the best length of linker to make sure that the bioreceptor is accessible to the analyte. So if the analyte cannot see, I'm not saying see because they don't have eyes, but if they are not accessible to the bioreceptor that you put on top of the sensor surface, then it's difficult for them to interact. Okay, that's the easiest way to understand. Okay, and if you look at here, there is another. Okay, why there is just now is linker under the biomolecules. But there is also linker in between the biomolecules, right? Okay. This is what we call as spacer. Okay. So spacer is put there in order for you to space out the biomolecule. So if you look at these examples, okay, we put spacer. Okay, I put different way of because if you don't put spacer, again, the issue with proteins, they love to tangle with each other. Okay. If you remember the word tangle, you can remember as the word tango. They dance. Okay. So in order for to separate them from tangle with each other, we have to put a spacer. Okay. So you can see how difficult it is. Okay. You don't see this actually. You don't really see this on top of the your sensor. Um, anyone has I'm not sure. Anyone has experience testing glucose using glucose meter? Anyone? No, don't worry. I'm not saying you that you're diabetic or what. But anyone has test glucose using glucose meter? Or observe your parents or uh, anyone? No, also. Okay, what the testing is done by getting the finger prick blood. Okay, some blood from your fingers, and then you put on top of the uh, glucose tester. Okay, so you might be thinking that it is an easy process. You put the blood there, and then you end up getting, well, the reading, whether your glucose level is good or your glucose level is above dangerous level. You might be thinking, yeah, it's quite easy. There's nothing. No, you don't see all this. You don't see the bioreceptors. You don't see all this kind of chemical modification on top of the tester. You don't see that on the strips before you put inside the glucose meter. But these are all there. These are all there because if you don't do that, then you have difficulty in getting a good signal. Okay, so let me continue. So now, effect of kinetic. Okay, so it's quite easy. Effect of kinetic. Usually, the main factor is temperature. Okay, uh, you have to use a specific, not to say specific, suitable temperature. Okay, for example, 40 degrees. Probably starts from 37, 40, or 45 degrees. Okay, that's where all the biomolecules are actively moving. So that is the effect of kinetic. You don't go beyond 80 degrees because that will start to denature, kill. Well, the word is denature. The proteins might be denature, means that it is breakdown, okay, broken down into molecules. So this is easy to understand because the word kinetic is something that you learn from your undergraduates. Okay. Another one, kinetics can be also um, controlled through stirring. Yeah. Okay. But stirring is not always that you can something that you can do because if you use portable device like the glucose meter or the test strip, there's no way that you can stir the whole thing. Okay, unless you're working with vials where you can stir the whole process. But the temperature is something that you can control. Huh? All right, so kinetics is very important as well. Okay, and we control through temperature. This one we have discussed the density. Again, this is the temperature. Okay, I'm not talking about the assessment now. Let me show you something else uh, about the end slide. Okay, where is it? Oh, okay. Mhm. Mhm. All right. I just want to show you some examples of startup. Okay, that is involved in the. Uh, okay. Let me find the slide first. Just a moment, yeah. Okay, let's wait until the file open. Okay, while waiting for the file to be open, okay, I would like to mention a bit on the assessment. Okay. Uh, okay, just a moment, yeah. Okay. So the assessment, as usual, you have 70% of um, coursework, means that assignments, tutorials, those that you have experienced before. So of course, in order for you to fulfill all the objective of this course, you need to have two assignments, hopefully we can have 35% each. And then we have final exams, as usual, 30%. Okay. And I usually do final exam for this course because it's not something that you learn in molecular spectroscopy or atomic spectroscopy. You actually study some topics, and then you can answer some calculation, for example, like steady state. So in sensor technology, because it is something new to you. So I understand if I ask you to sit for a closed book exam, you have to memorize a lot, and there are certain concept that is new to you. So I don't want this to, like, um, you resent this course because of this. Okay, I want you to. I feel that you should be getting some important knowledge for your future if you wish to explore this topic. Okay, that's my goal of you and in this class. So usually what I did is an open book exam. So if you remember your research methodology, is an open book exam. So I did this for sensor technology as well. But it will be like a different types of question, of course. And then since the issue of chat GPT and all that, there is some difficulty for me especially to draft an open book exam. So previously, even though it's open book exam, it requires you to think, to construct, okay, to give your ideas. So now the open book exam concept will be probably a bit more difficult. If because of the chat GPT and those kind of software, because you can actually um, generate the answer from there, and it's a big task for us to check the whether you are using chat GPT or whatsoever, one by one. So the answer, the question will be more on constructive answers, meaning that it will be exploratory. You think about it, or you try to come up with your own solution. So those kind of things. But I also want to give you an alternative. If you want a closed book final exam, this will be on you. So if it is a closed book final exam, it will come from the whatever that we have discussed, and of course we will discuss in future. Means that you have to memorize some facts, no calculation, but you have to memorize some facts. So I'm giving you opportunity, since everybody here is today is here. Sorry, everybody is here today. So you can give me your consensus whether you want a closed book examination or an open book examination. So what I'm saying is an open book examination, it will be probably a bit difficult questions, but a closed book examination will be the one that I have lectured. Okay, you have to like memorize some facts and then draw something, explain something. Oh, you want to decide next week? Yeah.
That's rough. I think can we decide a little later on,
Okay.
or probably poll on the group or something?
Yeah. Okay. So
Thanks.
okay, for that one is for final, yeah. And for assignment, so I will be giving two types of assignments, two different kind of assignment. One is of course individual, where your effort is individual based, and the other one is group based. So I will give the detail by next week. Okay. For the first one will be group assignment because I hope there is going to be less work for you to be done for the group assignment. Uh, don't worry, because of course assignment is an open source. You can, so it's a case study. You must be able to differentiate this course from other courses that you have taken before. Like statistics course is more on calculations, formulas, but this one you don't have formulas, but you have uh, some integrated information, okay? But your understanding is very important on this matter. Okay, so I'm sharing this one just to uh, share with you the status of um, biosensors. Okay, uh, I have shown you some examples on these types of sensors before. Okay, so let me fix this. Okay. All right, so this is the one that I have shown you before. This is the, I recall, evolution, evolution of sensors. Okay, they have shown from benchtop machines that currently you are still using. Okay, you have your chromatography, you have HPLC, GC, GCMS, where you do the analysis. Okay, but using biosensors or chemical sensors, this benchtop is actually miniaturized into something portable. So this is still being used, like if you're using glucose sensor or cholesterol sensor that you can buy from the pharmacy. Okay, so this is still in our era. But then you have this a new one which actually has been developed well, but not in the market yet. Something wearable like smart glass, your clothes, uh, the nano size, micro size sensors, and even implantable or edible. And there's a lot of this being developed, and probably people has not yet convinced with the performance, but you're starting to wear that now, which is the smartwatch. So smartwatch is some kind of wearable sensors, but it's not chemical sensors, it's physical sensors. Okay. So this is giant companies, yeah. Some giant companies like Abbott. This is Siemens. Okay. So if you look at this is a sensor for because there are those who has the problem of blood clot. Their blood seems tend to clot. So it's very dangerous condition. They have to monitor their blood clot issue. And imagine that you have to go to the hospitals every time to take blood. So Siemens has developed this sensor to check on the this issue, the blood clot. I don't know how it works because yeah, I don't have access to these machines, and but it is there in the market. Okay, and okay, let me go back. So this one, uh, okay. So Profusa, okay, this one is what we call as it's not wearable, but it's patchable. You can just patch it on top of your skin, and this you can analyze oxygen, glucose, lactate, urea with this. So I'm not sure whether this is in the market, but this one is already in the market. Okay. And you can imagine if you can have right now the glucose sensor, even though it's small, it is still bulky. You have to bring uh, the strip, you have to bring the glucose meter. If you don't know how it looks, please do look at the glucose meter in the pharmacies or online. So imagine that if you can have a portable device with the size of credit card, okay? So you can test not just glucose, but you can have different kind of analysis. So this one, let's say for glucose, this one for triglyceride, and this one for other types of cholesterol. Okay, so you can have this possible if you are using a biosensor. So this one also not in the market. It is under research. Okay, so I think this one I have shown you the examples of how mask, yeah, can be used to detect disease such as SARS-CoV-2. So you can see that the strip, this is the strip, okay, that changes colors when it is exposed to your breath. So it's a breath analyzer. All right. So this is an example. And this has been developed by MIT. Okay. And there is a research institute combining Harvard and MIT called Broad Institute. Yeah. So this is happening now, and they are much more advanced. The one that I studied is during the COVID, but they are much more advanced now. Okay, so I think I talked about enos before, but we haven't discussed anything about enos. Well, this is something that I always love to show people. Okay, this is Joseph Wang. Okay, very prominent figure in biosensor. So once upon a time, before he tried to develop called smart underwear. Okay, so it's not just smartphone, there is smart underwear. Why they develop this? They want to help the military, the army. Okay, so if they are under stress, means that it is in war condition. So there is a changes of liquid being secreted. Yeah, there is a changes, especially because this is underwear. So you can imagine the liquids, the sweats, changes in the underwear. So this will trigger. I mean, can be monitored in the headquarters. So probably soldier A is under duress, is under some, they need help. So helps can be given straight away to this particular person. So if you're, I mean, if you're short, you're sick, or you 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 don't have the capability to call someone. All right. So if you are, let's say, in the war, and then you are monitored at the headquarters, and somebody spot that you are in like a serious situation, then somebody can deploy help to you. So this is the goal, but I think they are not, it was not successful. I don't know for what reason. I never heard about this smart, smart underwear. All right. I don't know about the project. Probably it is secret. Probably I don't know. Okay, this is not updated. Okay, this is 2022. Okay, you can now it's more than that. So the value of the market, yeah, because why? People are getting more conscious about their health. Yeah, they would like to be tested. and then they want to make sure that all goods, cholesterol goods, glucose, and all things. But time for us to go to the hospitals, to go to the clinics, is something that requires you to go there and you have to wait, right? So by having what we call as home healthcare diagnostic, okay, this is actually biosensors. Yeah, they are biosensors, and they're also point of care testing. Point of care testing means that some patients cannot be moved. He or she is in the bed. You have to do the testing there and then. For example, at the bedside. So if you have a bulky device, then it cannot be done at the bedside. So you need to have this biosensor or chemical sensors at the bedside. So that is what we call as point of care testing. So home diagnostic is something that you can buy and then you can test at home. Let's say I suspect that I have dengue, then I buy and then I just check, just like you test your COVID. Okay, so you can see even it is 2022, it is the market now is billion. So now they have another market study and the value is much higher. So this is something, if you are interested in, it is very good. The color is blue and red. So food industry is actually even smaller. Okay, all right. So this is, yeah, Ani, for those who watch Korean movies, you know him. Okay, so SD Biosensors is very prominent company, okay, very big company in manufacturing test kits. Yeah, they have a lot of test kits. If you Google them, they have a lot of test kits, and they keep developing a lot of test kits up until now because now people are due to COVID, they know about test kits. So now they are asking for more. If there is test kit for other diseases apart from COVID-19. So this is a very big company and with very big market. And there are also a lot of startups, okay, now working on in biosensors. So I'm just trying to show okay, this is something that we have discussed, how big the biomarker, the biosensor is, okay, so that you know where this subject place. If you learn about this and if you're interested in the future, then you can probably explore during your PhD, or if you're working with company, pharmaceutical company, then you can explore this. Yeah. All right. I think we should stop now. I'll see you at 8 o'clock. All right.
Okay, Prof.
All right.
Thank
All right. So we have discussed about the basic principle of biosensors or electrical chemical sensors. The basic means the structure, the fundamental. And then we have discussed the the receptor, the bioreceptor. We have discussed DNA, antibody or immuno. And the third one is aptamer. So we have discussed these three. And after that, we have discussed the chemistry, the attachment or the immobilization chemistry. So we have discussed some basic chemistry. And then also we have discussed some factors, especially related to the surface of the sensors that you should be aware of. And the kinetic related to temperature. And also, of course, if you wish to read more is on pH, yeah, the effect of pH towards the condition. So not so many of like concentration, okay, as long as you can control, remember the density of the biomolecules, whether you need a spacer to control the density, or you need to use linker, how long the linker, okay, to again make sure that you have a very good immobilized bioreceptor. So those are something should actually complete you if you start to work with sensors, particularly biosensors and chemical sensors. So now we are moving to the next section of sensor, which is the transducer. So I actually, basically, I have shown you the example of electrochemical based DNA or electrochemical based immunosensor. And I also shown you example of electrochemical immunosensor, optical based immunosensor. So optical, usually we are using colors, UV, visible region, or fluorescence. Okay, there are others as well. So for electrochemical, we're talking about current, voltage, potential. There are impedance as well. Okay, so this is what we call as transducer. So this is electrochemistry. And the one that usually the technique that we use, it is called uh, is potentiometry. Okay. And voltammetry. Okay. So I'm not going to, as I mentioned, I'm not going to discuss detail on the techniques. Enough for you to understand. There is another M here. Enough for you to understand the basic, so that when we discuss about biosensors or chemical sensors, these are the available techniques that you can use. So I'll be focusing on voltammetry. Okay. So if you remember your chemistry before, okay, you have galvanic cell, and electrolytic cell. I don't know whether you use this term before during your undergraduate. Okay. So Ahmed, since you have gone through the electrochemical subject before, so what's the difference between this galvanic cell and electrolytic cell? This is
Gal-
basic. Yes, Ahmad.
cell, دكتور.
So what's the difference between this galvanic cell and electrolytic cell?
I don't know what's galvanic cell. I don't remember. Electric cell, it's okay, but galvanic cell,
You had never heard of it. So what is electrolytic cell?
electric cells that we cells can we use it in circles or in device to uh, I don't know how to say it exactly. I'm really
Okay. All right. So this is basic what we have known probably during school, secondary schools, or probably if you're taking basic electrochemistry, electrolytic is, for example, is water electrolysis. When you provide some voltage, okay, to water, you can separate the water into hydrogen,
oxygen.
yeah, oxygen. So those are what we call as electrolysis, electrolytic cell. You
Yeah.
need to provide the the current or the voltage to the system in order for the chemical reaction to happen. Right? In this case, the chemical reaction is splitting of water into hydrogen and oxygen. But galvanic cell is what we call as spontaneous. Okay, where we mix when we mix two chemicals. For example, we mix two metals. You remember, this is quite common where you put spoon. Sorry, that one is not, that is electrocoating. When you put two metals solution, and then they automatically undergoes reduction and oxidation. So I hope that you can still remember the word reduction, receive electron, oxidation, give out electron. Okay, so the word oxidation, being oxidized, okay, that happens spontaneously, means that when you mix the solution with salt bridge, okay, I'm not going to discuss what is salt bridge, at least you try to remember. When you mix, let's say, argentum chloride in one beaker, and then you have another copper nitrate in one beaker, and then you put together the salt bridge, there is a spontaneous reaction, one being oxidized, one being reduced, according to the electrode potential of that particular metal. Okay. So those are very basic that you have learned in undergraduate level. If this is actually basic chemistry, it's not under electrochemical subject per se, but it's basic chemistry that you have to learn about this reduction and oxidation. Okay. So when we talk about voltammetry, we are talking about the electrolysis or electrolytic cell. And potentiometry, you are talking about galvanic cell, meaning that when we, for potentiometry, when we have different, probably different concentration of H plus, let's say. We have different concentration of H plus, okay? And then automatically there is a potential difference. So you don't actually need to put current or voltage to the system, because automatically there is a difference in H plus concentration. Then you will observe a current difference or a potential difference. Okay. So this is the concept. Okay. Potentiometry, the best example is pH meter. Okay. When you put the probe of pH meter inside whatever that you want to measure the pH, the buffer, and you get the reading of the pH, right? It might be pH 7, pH 6. So those pH are actually initially based on voltage or potential generated from the difference of H plus in the probe versus in the beaker. Okay, so the difference of concentration of H plus in the probe, pH probe that you use, where I can see. Okay, when you dip it, okay, so there is certain concentration of H plus in the probe, fixed, and then when you dip it inside the beaker, there is a difference in concentration of H plus. So the difference will generate potential, and that potential will be translated into pH. Okay, so actually pH meter is a chemical sensor. You detect pH using pH meter, so it's a chemical sensor. So the one that are being used a lot right now for biosensors is voltammetry. Okay, so I'm going to introduce to you the basic setup for voltammetry. Okay, so remember voltammetry, it's not potentiometry. You need to supply voltage to the system. Okay, just now I mentioned about potentiometry, you do not need to supply voltage because the reaction itself will generate potential difference spontaneously. Okay, so you do not need to supply voltage. But for voltammetry, okay, you need to supply voltage in order for the reaction to happen. Okay, so you imagine this is where you put the chemicals. Okay. All right, so these three electrode has to be connected to a machine called potentiostat. Okay, so this machine will supply voltage to the cell. This is what we call as the whole thing. It is what we call as electrochemical cell. Okay. So in here, we can put all the chemicals, of course, in solution form. Okay, so from there, if we supply voltage, then there is a possibility of chemical reaction to happen if the voltage is enough. Okay, so before we proceed to that, this is the basic structure. We have reference electrode. Working electrode is where the reaction, the chemical reaction happen. Okay. The counter electrode is to complete the circuit. Okay, the complete the circuit between working, where is working? Yeah, this is working, and this is counter. Because if we understand about electrical, it has to be completed. The circuit has to be completed. You cannot just have incomplete circuit. If there is no complete circuit, then the current will not move. Okay, the potential will not move. There will be no current also. Okay, so counter electrode is to complete the circuit, whereas the reference electrode, basically it will stabilize the voltage. If not, then you have fluctuated voltage. So this is basically, I mean, if you can Google, this is something that you will find some definition of what is reference electrode, working electrode, and counter electrode for voltammetry cell. So in general, electrochemical cell is the same thing. Okay, so now this is the working enlarged working electrode. So what happened is, if you put some chemical reagents here in the beaker, okay, so you imagine that the chemicals, if the chemicals are electroactive, yes, of course there are a lot of chemicals, especially organic chemicals, they are not electroactive. So if you put organic solutions in the beaker, even though you supply voltage, there will be no reaction because it is not electroactive. Okay, so for those electroactive material, for example, metal solution and some others, there's a lot of salt solutions that is electroactive. So if we put it inside here, inside the beaker, and then we supply enough voltage, okay, so there is oxidation and reduction that happen. Okay, not the compound, the material, the ions inside the metal solution, for example, one will be oxidized and one will be reduced. So they actually move here. You can see there is electron. Okay, so the one that being oxidized will give out electron. Okay, and the one that being reduced will receive electron. That is basic. Yeah, for example, if you have copper 2 plus, it will receive 2 electron, forming copper, 2 copper, forming copper, 1 mole of copper in elemental form, which is solid. Okay, so this is reduction of copper. So if it is oxidation, it is vice versa. Copper solid being oxidized, it will give out electron plus producing copper 2 plus. So this is copper in elemental form being oxidized to copper 2 plus. Okay, so this is the basic, right? Question you can ask. So now from here, from this setup, okay, it looks bulky. So actually now this is how it looks like. Even now it is much, much smaller electrode. This is still the size of, yeah, the actual size of electrode that is actually this size. Okay, and now I have shown you some example just now, yeah, the credit card size. So those are, you can imagine electrodes now is miniaturized. The size is very much smaller and can be used on, you can imagine just now, you have like lenses, okay? You can put the small size electrodes on this kind of device, okay? So it's about engineering. How good your engineering facilities to make small things. But this is what we call as screen printer electrode. So imagine from here, this particular size has been miniaturized into disposable, okay, electrode. But still you have the main elements, reference electrode, working electrode, counter electrode. Yeah, the same structure. Okay. So this is basically voltammetry. So this is what I have mentioned just now. Reference electrode to stabilize the background potential. Counter electrode completes the circuit. And working is where the reaction happens, the oxidation, the reduction happen. Okay, so most of the time when we do research in electrochemistry, this is the one that we develop, we work on. Okay, so this one is standard, this one is usually standard. Okay, so another factor, another material that is important is what we call as supporting electrolyte. Okay, so in here, I have to rub it off. Okay, so in here, we have to put, of course, the chemicals of interest that we want to study, plus what we call as supporting electrolytes. Let me finish the writing. Okay, supporting electrolyte. Okay, so there are, of course, examples of supporting electrolyte, and usually is salts based, concentrated salts, because this electrolyte will help the movement of, you can see the oxidize, the reduce, they have to move towards the surface of the sensor. So supporting electrolyte will sort of provide better movement, will help the mobilize the ions going towards the surface of the electrode. If there is no supporting electrolyte, it's quite difficult for the reduction and oxidation to happen. So this one no need. This is the basic circuit, yeah, that is as the voltammetry. Okay. So what is voltammetry? In definition, is electrochemical method in which information about an analyte, okay, the word analyte is there, the one that you wish to analyze, is obtained by measuring current as a function of applied potential. Okay, so remember when we talk about voltage, when we talk about voltammetry, we have to supply voltage for the reduction and oxidation to happen. Okay, so after the oxidation and reduction happen, you can get current. Okay, so that is basically what voltammetry. So the current change is the one that giving you the indicator whether there is reaction happen or there is no reaction happen at all. Okay, so that is voltammetry. So this is what happened at the surface of the electrode. Okay, again, same things happen. You have being oxidized and the one that being reduced. They have to move towards the surface of the electron. There is electron transfer happening on the surface of the electrode. And then, of course, one will be reduced and one will be oxidized. So here you have the supporting electrolyte. As a medium. So the movement of the being oxidized and being reduced can move towards the electrode. Okay, again, there are some factors. So remember, sensors itself have factors, sensor surface, but the electrochemical technique as well has factors that has to be considered. One is the mass transfer, okay? It seems that if you look at the vials or the the cell, it is very small. And then we expect, we usually expect, why is not, okay. Okay. We expect the oxidant and the reductant will easily move towards the electrode, right? We expect, you can just run to the surface of the electrode. Now, it doesn't work that way. It's a molecule, it's ion, yeah? So you cannot just expect them to move easily, okay? So you need some motivation to move to the surface of electrodes. So it seems that it is very, not that far, right? It's very, the path is very short, but it's a big factor, okay? It has to move. So that's why one thing, mass transfer, one of the things that we can do is like stirring, providing the just now electrolytes and other things that you to make sure that it moves to the surface of electrode. And the second one, when after they move and they have arrived the electrode surface, not election, this is wrong word. The electron transfer must happen at the surface of electrode. Okay, why is it election? The electron. Okay, this is also something that you have to think about to make sure that the electron transfer will be very fast process. Okay, and that's what we do. Okay, Remember about the nanomaterial, all those nanographene, the CNT, those things that we can put on the surface of electrode. Okay, we put all those sorts of new materials. Yeah, I'm just putting something. This will help to enhance the electron transfer. I mean, the reductant and the oxidant is there, but the electron transfer must happen very fast. So you need to add some material on top of the electrode so that the electron transfer can be very fast. Okay, so other things about is, okay, the solution itself, homogeneous or heterogeneous, okay. Chemical reactions happen. Desorption, okay, all right. So this sum up the process in the voltammetry. You can see surface area. This will sort of give you, if you have a large surface area, means that a lot of electron transfer will happen. You will get good current, for example. Porosity, surface condition, geometry. So that's why we work on the working electrode, the characterization of the working electrode. And then how the reductant and the oxidant will move. Okay, there are certain type of movement, diffusion, surface absorption. So those are theories that we can choose to control certain parameters so that we have diffusion movement, surface movement, okay? Electrolyte, pH, solvent, and then we can also work with temperature, okay? And of course, how much potential we supply to the system also works. Very important to work with, okay? So these are the things in voltammetry that you can think of, okay? That you can study. Okay, so I'm not going to discuss this. So imagine this is where that we have discussed electrochemical biosensors. Okay, but I'm not going to discuss this today because it's going to take a lot. Okay, what I'm going to discuss before we can discuss about the indicator is a bit on the DNA indicator. Okay. Okay, take a deep breath. Okay, we're going to revisit the hybridization. Okay, right. Do I have any other colors? Okay, so remember again about the probe and the target DNA. And then I mentioned about how we measure the hybridization. Okay, we need to measure whether it's 100%, 50%, etc. Okay, so I remember that we talk about indicator. Okay, if we choose electrochemical method, then we need to have indicator that is electroactive. Okay, so the black material that you see here, these are what we call as hybridization indicator. So if we are using electrochemical technique, we must use electrochemically active indicator. Okay, so I hope that you remember this concept. We want to know whether you are positive dengue or negative dengue based on DNA. So if it is 100% hybridized, so you are confirmed, yes, you have dengue. But if it is like 10%, then you're not confirmed. But how do we know the 100%? And how do we know the 10%? Is by using this indicator. Okay, we need to put the indicator into the system. Okay, so there are many types of indicator. Let me rub it off. Specifically for DNA. Specifically for DNA. Okay, DNA based biosensor. So it is called intercalators. This one, intercalators. Okay, they are what we call as groove binders. These two is groove binders. Groove binders. Groove binders. You can see that they are at the groove. There are major groove and minor groove. Okay. So what happened is for these groove binders, let's talk about groove binders first. All right, just a moment. Where is it? I don't know what happened to this. Okay, it's okay. Now, we're talking about groove binders. Okay. If we look at the structure of the DNA, here, this is what we call as groove. Okay. So we can have this indicator in the form of groove binders. So when the DNA hybridized, okay, and then we expose the whole thing to the groove binders, okay. If there is a good match, the binders will bind themselves to the groove. But if there is not good match, for example, if only 50%, then 10%, then the hybridized structure, the helix, double helix structure that you see here will not be formed. There are not many groove that the groove binders can attach itself to the system. So that will be the base of how much current can be generated by the system, because the groove binders, they are electrochemically active. Okay, so they will generate current. So if you like have a lot of groove binders attached to the DNA, that represent there's a lot of hybridization happen, means that the percentage of good hybridization, perfect hybridization is there. Okay, but if we have less hybridization, meaning that less groove binders attached to the double helix DNA, meaning that you have less hybridization. So that is translated as well into current. So more groove binders, more current, less groove binders, less current. Okay, so that will be groove binders base indicator. Let me solve why my okay, I dah dapat balik dah. All right. Okay. Are you okay with that? Okay, it's a basic. Right, now, the other indicator that is suitable for hybridization indicator is what we call as intercalators. So just now is groove binders, now intercalators. Intercalators, they intercalate inside the double helix structure of the DNA once it is hybridized. Okay, so you can see that the same procedures happen if you have a good complete hybridization, then you have a lot of intercalators inside the double helix. That is shown as a higher in current. Okay, So if there is less intercalators, meaning that less hybridization, so the current, yeah, sometimes it is low. Yeah. So this is what we call as electro sorry, hybridization indicator, but it is electrochemically based. Okay. So indicators for electrochemical technique has to be, of course, electrochemically active. Okay. So I'm going to, to give you examples. Yeah, they are organic compound, metal complexes, and metal nanoparticles. So they are the indicators. Yeah, that is electrochemically active. Okay. For example, we have what we call as methylene blue. This is the structure of methylene blue. And methylene blue is an example of intercalator. Okay, you can see the benzene ring. So they actually intercalate inside the double helix structure. And they have this hydrogen bond, okay, with the nucleic acid. Okay. So one is methylene blue, just an example. Okay. This is another compound, another intercalator. You can see ferrocene, yeah? Ferrocene base. There are also benzene ring, yeah? Okay. But usually they have flat structure, and I'm going to show you this is metal complexes, ruthenium complex, and they are also intercalators. Okay, they slot inside the DNA. Okay, and I'm good. Okay, this is example of groove binders. You can see the main characteristic of groove binders. They are crescent shape. They have this crescent moon shape. They have this shape. So if you understand just now, the groove binders, okay, they have to need the suitable shape to attach to the groove, whether it's major or minor groove binders. So the characteristic of groove binders is crescent shape. Okay, so you can see this is how they interact with the crescent, the groove, the crescent shape. They interacted with the groove of the DNA. Okay, right. I'm not going to discuss this one. This is the current. Yeah, you see, this is groove binders, and then you can see if we have a lot of DNA, there's a lot of groove binders, and the current is high. If there is less DNA, means that the double helix structure, then you have less current. So don't bother about this, yeah. So I think that's it. Okay. So this one is optical. So I think what we can do is to discuss the optical technique first before we discuss the indicator for optical. Yeah? All right. Okay.